Well, hello and welcome to Math 315 Analysis and Topology, and this is the first recording for section 8, in which we're going to look at power series and Taylor series. So we begin by a simple example. We're going to look at this geometric series. So we look at this standard series 1 plus x squared plus x cubed and so on, and we can write that in sigma notation as sigma k equals 0 to infinity x to the k, because x to the 0 gives me 1, there's the first term, and so on. Now this is a geometric series. The first term is 1, the common ratio is x. So as we've done before, we can find a formula for the nth partial sum, s sub n, which is just 1 plus x squared up to plus x to the n. And there are n plus 1 terms, notice, in this sum, so I just use the usual formula. So it's a into, a is 1, into 1 minus r, that's x, to the number of terms, there are n plus 1 terms, divided by 1 minus x. So this is the standard formula for the sum of the geometric series. Now, as n gets larger, this term, x to the n plus 1, well, if x is bigger than 1, like put 2 in for example, then this is going to become very large, and so the series won't converge. On the other hand, if I take my x to be between minus 1 and 1, then the expression x to the n plus 1 will become very small. This is our standard argument about the limiting sum of a geometric series. And that means the infinite series will have a limiting value of 1 over 1 minus x. Now, in the case where at the two extremes, in the case where x is 1 or x is minus 1, in the case of x is 1, well, we just get 1 plus 1 plus 1 plus 1 forever, which obviously diverges. In the case of x is minus 1, then I'll get 1 minus 1, and then minus 1 squared is plus 1, and minus 1 cubed is minus 1, and so on. And this one here is boundedly divergent. It doesn't converge to anything. And so, in both cases, the infinite series doesn't converge. Now, this series above is an example of a general class of series, which we're going to call power series, because they involve powers. And these have many applications, in particular to differential equations, but in lots of other areas as well. And we'll see some applications of this a bit later. So in general, a power series then is an infinite series that has this shape, this form. In the example above, the ANs were all 1 and the B was 0. But in general, there are going to be some numbers where the AN is some sequence, times x minus something, b is some real number, all to the power n, and we take sum from n equals 0 to infinity. And of course the basic question is going to be, well, when does this actually converge? When does it make sense? Now, just to get some terminology, we say that the series has centre b, that's this number here, since when you put x as b in, all the numbers are 0, all the terms are 0. And we're going to call that the centre of the series. By the way, sometimes the series may not begin at n equals 0 for obvious reasons in the context, so it doesn't necessarily have to begin at 0. Most of the time it will, but sometimes not. So just note then that these power series are really like polynomials of infinite degree, is one way of, polynomials aren't allowed to have infinite degree, but you can think of them as just like polynomials, but they don't stop, they've got infinite degree. So an example of that is something like this sum here. Now here I don't begin at 0, obviously, because I'd be dividing by 0, so this sum begins at n equals 1. So sum x minus 3 to the n over n. This is a power series, so the sequence, the coefficients are given by 1 over n, that's the a sub n. And the centre of the series is at b equals 3. Now the obvious question that arises is, for what values of x does a given power series converge? After all, the one we looked at right at the beginning only converged if x was between -1 and 1. Now this of course will depend on the value of x that we choose. So for some values of x this will converge, and for some values of x it won't converge. You can think of then, this is another way of thinking about these things, you can think of a power series like this, of this form, as defining a function. So we can, x is our variable here, the sequence ANs and the B's are fixed, x is the variable, so we can think of this as a function of x. So finding where the power series converges is really the same as asking for the domain of the function fx equals this power series. Just another way of thinking about this. And indeed it's going to turn out that one often can define functions in terms of infinite series. So we saw in this example here we did before, we started with, that this power series given there converges if x is strictly between -1 and 1, but it diverges outside of this range. That is, this series converges in the open interval -1 to 1. So we can draw a little picture here for this. So if we're thinking about the domain of this function, then it converges, the domain of the function is this bit in here. It converges provided we take an x value in there. Now this interval is called the interval of convergence. So we're going to generally get intervals, it's called the interval of convergence. Another way of saying this in terms of our function analogy is to say that the function f of x equals this has domain -1 to 1. That's the interval, that is the domain of this function. Moreover, you might like to try this if you were to get the computer to replace the infinity with, say, 100 or something, and get the computer to draw this, then you'd find that the picture only works between -1 and 1. And in fact, you'll get asymptotes at the two endpoints. Now, we're going to be rather careful here, since there are two variables going on in all the stuff we're doing. There's the summation variable here, which is k, or sometimes it'll be n, and that's the summation variable, whereas the real variable is x, which is the x in here. So just be careful not to confuse the two. Now the distance from, just to get some more language and notation going here, the distance from the centre of the series to either endpoint of the interval is called the radius of convergence. So the name, by the way, why are you talking about a radius when it's an interval? Well, the point is the name comes from the fact that when you're dealing with power series in the complex plane, which we're not going to do at all in this course, if you're doing complex analysis, this is what you do, then the interval becomes a circle, and hence the use of the term radius here. So in reality, there's a lot more going on here. We've got an interval, but in fact in the complex plane you're getting convergence inside of a circle here. And so it makes sense to talk about the radius. But we're not going to be doing any complex analysis here, of course, so that's just to explain why we use this word radius. So in the first example, the radius of convergence then is 1, because there's the interval of convergence, and the radius is half the length of this, which is 1. Now it turns out that every power series of this form, and this has got width centre, pardon the spelling mistake there, width centre 0, either converges for all real x, in other words it works for every value of x you can put in here, or more commonly it'll converge on some interval of the form -r to r with radius of convergence r. That is, it's going to look something like this, except you'll get r here and not 1. So that's typically what's going to happen when we've got these series that are centered at 0. So given a power series, the question arises then, how do we find this interval of convergence? and hence how do we find the radius of convergence? We go for the interval firstly, and then we can just read off the radius of convergence. For us, the interval is going to be the more important point in this course. Now, one approach, in fact the only one we're going to be dealing with here, is to use the ratio test that we did in an earlier chapter. There are other ways of dealing with these, but for us we're only going to ever do analyse these using the ratio test. So here's an example. Here we're going to apply the ratio test to this series, and we're going to find the open interval of convergence. And so here is the solution of this. Now you remember the ratio test, we looked at this before when we were doing infinite series. Now we've got an extra problem here because we've got x's in as well as the n's. And what we did was we looked at a sub n plus 1 over a sub n, and we took a limit of this. This time we're going to take the absolute value of this. That's because of the x here. We didn't need the absolute value before because all the terms were positive, but now the x could be negative, and so we want absolute value here. So I'm going to use the ratio test again. So a sub n plus 1, where I see n, I copy n plus 1. And then I'm going to divide by a sub n, and again, as we did before, we're going to just invert and multiply. So turn it upside down and multiply. And don't forget what absolute value is now. Now remember, the n's are all positive. So out of this, I've got an n plus 1. I've got an n on the bottom, so there's n plus 1 and an n on the bottom. I've got a 2 to the n plus 1 on the bottom, a 2 to the n on the top. So I can cancel this into this, and I just get one single 2 survives. Now these are all positive, so I don't need absolute value here. Now that's doing the n bits. Now do the x bits. You've got x to the n plus 1 over x to the n, and that's just x. And I do need absolute value here because x could be negative. Now we take a limit of this as n goes to infinity. So as n goes to infinity, we're going to take a limit. So the x just stays as x, nothing happens to it. It's the n we're taking the limit of in the ratio test. And again, you could divide into here. This is a half plus 1 over 2n. And in the limit, that goes to a half. You should just check that little limit there. Now the ratio test, that's what the ratio test says you do. You look at this ratio. I've done that. You take a limit as n goes to infinity. I've done that. And then we said before that if that limit was less than 1, then we have convergence. So what I do here is I'm going to make it less than 1, and I'm guaranteed convergence. So just note that step there. We look at the absolute value of the ratio, an plus 1 on an. Simplify it, take a limit, and then I'm going to force that to be less than 1 for convergence. Now just rearranging that, I'll pull the 2 up here. That says absolute value of x is less than 2. That says minus 2 is less than x is less than 2. So the interval of convergence then is the open interval minus 2 to 2. We're not going to worry too much about we will worry in a minute about what happens at the endpoints, but at the moment that's all we're concerned with is the open interval. Again, that means that if you want to think of this in terms of functions, it says the domain of the function f of x equals this is this interval here. And we'll see that doesn't work at the endpoints anyway, so that's the domain of the function. And so we could also say that the radius of convergence, if we wanted to, we only asked for the open interval, but the radius of convergence will be just half the length of this, so that will be 2. That will be 2. Now, note that the ratio test doesn't give you any information when the limit is 1. When the limit of that an plus 1 over an, if that limit is 1, we've seen before you get no information out of that. So this method that we're using will ensure convergence on an open interval, but will give no information about what's happening at the endpoints. Now, to see what's happening at the endpoints, we have to look separately at these and use the method from, well, not the last, perhaps from a previous chapter, to test for convergence. Now, in this course, we're only going to be interested in the open interval convergence. I've just included one example here to show you what happens just for completeness, but I'm not going to expect you to be able to do this. We'll have to use alternating series when we're doing these often. So just to show you what happens here. So using that previous example, if we plug x equals 2, that was one of the endpoints, plug x equals 2 into the series, then we get n times 2 to the n over 2 to the n. 2 to the n's cancel, and I just get sigma n. Well, that clearly goes off to infinity. This is 1 plus 2 plus 3 forever. So the series diverges. Now at the other end point of minus 2, if we put minus 2 in, then I replace x with minus 2, I get that. Now I can peel off a minus 1 to the n out of here, times a 2 to the n, 2 to the n's cancel, and I get this thing here, which is, well, what's this look like? This is minus 1 plus 2 minus 3 plus 4. This doesn't converge either. This also diverges. So in fact the full region of convergence is still the open interval minus 2 to 2. So that's what happens if you want to look at the endpoints of the series. This is what you've got to do. But in this course we're not going to bother about looking at endpoints. We're just going to find the open interval of convergence. And we'll continue this in the second recording.